A very good morning. This is a continuation from lecture 2, week 8, because the file was too large. I had a problem in having it all in one slide. So this is a continuation. Now remember we talked about selection with threshold traits where in the earlier last slide. And what is threshold traits? They threshold traits actually exhibit categorical phenotypes and it's not continuous in their expression. Selection intensity when it comes to threshold traits is smaller and the performance is smaller. One example is fertility, right? So to understand more on the scale of liability in threshold traits, you can see that in this example, sampling from the top 95% of females, uh, if you look at the first figure, you could see that if this is the intensity, we select the top 80%, but the females are not so fertile. So therefore you want to increase the selection intensity, then you narrow down the chosen group and it's now to top 95%. So when you do this, you actually can cause liability. Why do I say this? It's because when you reduce the selected parents, the chances of you introducing only a very few females in the population, and therefore you're using less number of individuals as your base population, and this will cause in future inbreeding problems. So therefore, even though if you think of trying to be stringent, sometimes your intensity can create results of a lower results. So when we talk about generation interval is very important. When you're doing quaternary genetics, the genetic response to selection predicts how much better the next generation will perform compared to the current generation. Playing around with these components of formula of genetic gain will give you a feeling of how selection decisions can influence the response of the selection. So if you're looking at rabbits, jumping rabbits, okay, and you want to now look at the accuracy of selection, which is the influence of the predicted response to selection. The problem is you need to understand the genetic gain that we predict in the next generation. You always have to understand how long is the generation interval. So what do you mean by generation interval? If you look at this figure 4 shows from birth to birth offspring. This is where you see birth, then you look at where it reaches an adult, you have the performance test and selection, owned, that means they breed by their own, maybe half sieves, full sieves, then the mate and they have offspring. There's another different generation interval, same thing, mating, birth, offspring, performance of the test offspring, then selection again, this is where you impose selection. Again, birth offspring, mating, and birth offspring. This is already 2 generation interval, which shows more accurate. So it's the average age of parents of birth in their offspring, and they will produce the next generation of breeding animals. This generation interval facilitates to calculate the genetic response per year instead of per generation. So if you have a short animals with shorter generation interval, you try to improve the animal because in a year you can have 3 generations happening in the same year. Hope you understand that. So to apply generation interval in relation to realized response to selection, always remember this, that you are actually the one in control when you're working with population, where you actually impose selection, and the selection, you can see this is TS, the T selected minus T, and the population after mating of one selected parent, which is the T prime. All right, the selection response is R equals to T prime minus T. All right, and then heritability equals to R over S, or when you say response equals heritability over time selection response. All right, response to selection. This is a very important formula, and you should remember that. Now, why is it so important we started the lecture this whole week talking about selection and in an improvement program. Why is it so important for us to understand the response to the selection? So you must always understand breeding is about predicting the future. Okay, so predicting the genetic gain is about predicting future performance and evaluating breeding decisions. So genetic gain is determined by three main factors: phenotypic variance, accuracy of selection, and selection proportion. Now the generation interval allows to express genetic gain per year instead of per generation. Optimizing genetic gain will require a balance between increase in accuracy and decrease of the generation interval. Selection paths allow difference in selection proportion and accuracy of selection in males and females. And the decisions on intensity of the selection depend on the consideration of genetic gain versus rate of inbreeding. So when you impose indirect selection using indicated traits, where you can actually have a good solution for traits that is difficult to measure and expensive to record, like fertility, disease resistance, things like very difficult to see. Predicting genetic response to selection, assuming the lack of selection proportion, is very useful, but you need to understand about the accuracy. And lack of accuracy will cause you a problem in your selection. So you have to understand accuracy and selection. Now, you need to understand that corneal genetics is applied in a structured animal breeding program. Even in plant breeding program, it's also applied. Now, today we'll talk about animal breeding program. Number one, you need to define your production system. Once you define your production system, that's when you did your case studies. You define your production system. You define the breeding goal. Okay, you want to improve what growth, you want to improve fertility. So you define your breeding goal. Then you start collecting information, which is number three. You collect information. You want to collect phenotypes, family relationship, genotypes. You have all this information, because what information you collect will allow you to do that analysis. Then you determine the selection criteria. And in selection criteria, you have your genetic models. And genetic models is like North Carolina design, dye-allele design, which we cover in topic 9, and I've already put up the notes there. And how do you estimate the breeding value? Then we looked at selection and mating. In selection and mating, what we want to achieve is prediction of selection response. And what happens if you start mating and crossing with different individuals? Do you have the consequences of mating? If you now have a selection intensity of 95% threshold, what is the consequences of that? So this comes here. All right, then we move on to dissemination and structure of breeding program. Cross breeding. So do you want to do cross breeding to get heterosis effect, or do you want to have a structured breeding program like North Carolina design 1, North Carolina design 2, dye-allele design? So these are all called structured genetic improvement. Ultimately we want to improve genetic improvement, and of course we need to understand the diversity. That's through population genetics. So you can actually understand the genetic diversity of the population you're working from the very beginning, from base population right up to the next generation. So you must understand that we are now at year, and we will discuss about structure of breeding program and cross breeding programs in the next class. And finally, we'll reach the ultimate goal of improvement and genetic diversity. All right. Have a nice day. And for all the Muslim friends, I like to wish Salam Hari Raya. Bye.